Hey friends, welcome back to day 4 of my machine learning journey. Today we're going to explore feature engineering and how it impacts model performance using the Titanic data. But first, what is feature engineering? Let's define. Feature engineering is the process of creating new variables or transforming existing ones. This means that our models can better capture patterns in the data, and it's often the difference between a weak model and a strong one. Without further ado, let's jump into Jupyter Notebook. Let's get started. In this first cell, we're gonna import our libraries. In this case, we import our core Python libraries, in this case, Pandas, NumPy, Seaborn, and Matplotlib for visualizations. We're also bringing several different packages from scikit-learn library. In this case, we're gonna import for pre-processing, modeling, and data evaluation. Think of this step as setting up your toolbox before starting the actual build. Run the cell, and then we're gonna import our data that is built in within the Seaborn library. In this case, the Titanic data. This data set is small, but it's perfect for demonstrating the concepts here. Let's start with basic feature selections. I start by selecting some key features, in this case, sex, age, fair, class, embarked, sibling, spouse, parent, child, and alone. These features cover demographics, ticket costs, travel class, and family size. The target variable is survived, whether a passenger made it through the disaster. In this cell is where the feature engineering begins, and this is where we add new information for the model. First, I'm gonna create the family size feature. This case, what does it mean? Is the total people with tickets in a family group. In essence, we're gonna use the sibling, spouse, and parent, child, and adding that to cell. The idea behind this is that survival chances might change depending on whether the person was traveling alone or with family. Next, we're creating a new feature named is_child. How we're gonna do this? Basically, we're gonna do anyone that is under 16 is gonna be labeled as a child. Historically, in emergencies, children were often prioritized, so this could be a meaningful signal. Finally, we added a third feature, in this case, the fare per person, which is the fare divided by the family size. This is going to normalize the cost per traveler and might highlight socioeconomic status. Let's take a pause. First, why are we doing this? Tree-based models like decision trees and random forests are very good at splitting meaningful features. Crafting new features, we give the model better build. This is especially important in structured tabular data where raw columns often don't capture the full story. Let's run our cell. We're gonna address the missing values using drop-in-A, and we're gonna re-index the files based on the X. We're also printing the shape of the data set, and we're gonna display the header as a data print. Now we're on the pre-processing section. In this case, we're gonna split our features by numerical features and category. Here are the numerical features, which is age, fare, sibling, spouse, parent, child, family size, is child, and fare per person. Then for our categorical features, we're gonna do sex, class, embarked, and alone. For this section, we're gonna transform and scale our feature. We're gonna create two new variables, which is numerical transformer and category transformer, and we're gonna use pipeline with both standard scalar on the numerical transformer and also a one-hot encoder. As we discussed in previous videos, one-hot encoding means transforming label or categorical values into values of 0 or 1. We're gonna pre-process our data using the column transformer from scikit-learn. Now we're in our pipeline section. In this case, we're gonna create 3 different types of models: logistic regression, decision tree, and random. Logistic regression is our simple baseline. Decision trees are interpretable but can overfit, and random forests combine many trees for stronger generalists. So now we run our pipeline cell with all the 3 models, and now we're gonna do cross-validation. For cross-validation, I use a stratified 5-fold. This ensures that each fold maintains the same balance of survivors and non-survivors. Cross-validation is key for honest evaluation. It prevents us from relying on just one lucky train test. We're running our cross-validation here. We're using 5 splits, we're shuffling them, and also using a 42 for random state to be able to replicate the result. Here we're creating a model dictionary with all of our 3 models. We're gonna add that the results, an empty list for now, and we're gonna use a for loop to place all the results and append them based on each accuracy. Once we have the for loop, we're gonna create a data frame, a table, and save it as CV results or cross-validation results. Here we have our output for our three models. We can see here that the average or mean accuracy is between 79 to 82. It's consistent across all three. For the standard deviation for accuracy, it's about the same, a little bit lower on the decision tree in contrast with the random forest. The F1 mean or harmonic mean, it's about the same for across all three. And for the F1 standard deviation, it's higher on the random forest. For ROC AUC mean curves is going to be 85 through 87 with the lower value of 84. And our standard deviation for our ROC curve is going to be in the 0.03 to 0.0. As you can see here, the models are performing really well. However, random forest might be performing better. Now we're gonna visualize our results. In this case, I'm gonna overlay the ROC curves of all three models. This let us compare how well each one distinguishes survivors from non-survivors at different costs. Visuals like these are powerful because they make the trade-offs clear at a glance. Let's go over the cell. We're gonna train, test, and split our data, creating our variables here. We're gonna do a test site of 20% or 80-20 if you will. We're gonna stratify our data, and we're gonna do a random state of 42 to be able to replicate our results. We're feeding our data here on each of our different models using the X and Y trained datasets or split. Here we're plotting one figure with all the three ROC curves. We're creating a subplot with our size of 7 by 6 inches, and we're using the ROC curve display from scikit-learn, and we're basically adding each of the models, their variable. We're making that equal to our figure, and we're naming each one. For the plot, we're gonna do a line that goes from 0 to 1, and we're gonna label it change. As it says here, our title is gonna be the ROC curves, logistic versus tree versus random forest. We're gonna label our X as the false positive rate and our Y as the true positive rate. The legend is gonna be located at the lower right. Keep in mind that for this particular line, the legend, you might need to move the location to lower right, lower left, upper right, upper left, depending how your lines show up when you finish the visualization, because sometimes you can have the legend right where the data. I'm using a tight layout and also adding one more line of code to save the figure inside my documentation for my GitHub portfolio, and I'm defining a DPI of 150 and a tight layout as well. So now let's do that. Let's run this cell. Here you have it. We have our visualization here comparing all three models: logistic regression, decision tree, and random forest based on the Titanic dataset. At a quick glance, we see here that random forest proves, or it's arguably better just by a margin, in contrast with logistic regression, which we can see here is 86 versus 87. Decision tree did slightly worse, but not much. It's still higher than 0.80, which is always good for this type of models, this type of ROC curve. In this notebook, we saw how feature engineering, adding family size, its child, and fare per person can improve a dataset's predictive power. Then we compared the three models from simple logistic regression to more complex ensemble models and evaluated them with cross-validation and ROC curve. The key takeaway is this: models are only as good as the features we give them. Engineering features with domain knowledge can make a huge difference. If you found this helpful, follow along as I continue this machine learning journey. Next, we'll move into fraud detection with imbalanced datasets. Subscribe if you want to learn step by step with me. Thank you so much. Take care.